Hello, IME 145 students. Welcome to week 5 of our IME 145's lab presentations. Hopefully, you've been doing well in your face-to-face labs and your virtual Haas mill operator training. You've been enjoying the curriculum so far. But today, we're going to talk all about surface treatments, finishing processes. Then we're going to get into the world of geometric dimensioning and tolerancing, which is a huge deal out there in the world of mechanical engineering. So here we go. Surface treatments are really important because after we manufacture a part, we want to go ahead and maybe improve the part's service life, or if its appearance, or maybe its function, by changing the surface properties of the engineering material. And we can pretty much apply surface treatments to any type of engineering material out there, whether it be a ceramic, a metal, a polymer, or some sort of composite. Now, some treatments work well on some types of material. Some treatments work better on certain types of materials than others. And some surface treatments can't even be used on specific types of materials. So that's really your goal of this lecture, is to understand the different commonly used surface treatments out there in industry and what types of parts they can be applied to. So really, everybody's probably had this a carbon steel part, right, that you've maybe left out and it's rusted. And surface treatments can prevent it from corrosion and maybe make the life of that product last a little bit longer. But really, there's 3 major reasons for applying a surface treatment to a part. Number 1, you can alter the appearance, maybe change its color somehow, or its surface texture, or maybe you're just cleaning it and making it look better, altering the appearance that way. If you look over in the bottom right-hand corner, they're dipping those car bodies and they're cleaning the car bodies there. They're slightly altering the appearance there, but they're actually cleaning them before they actually paint the car bodies. Like you'll see that on the bottom right corner. Now, another reason you might use surface treatments are to alter the dimensions. Some parts maybe have a worn surface, and you need to go ahead and use some of these surface treatments that we'll talk about to build up layers and maybe rebuild the surface. You can do that. You can also add protective layers, like in the case of anodization or powder coating. We'll talk about those 2 types of processes there. So it adds some sort of protective layer to go maybe make the part a little bit harder on the surface, or maybe keep it from corrosion or corroding. Fixed mismachining. Sometimes you have a really expensive workpiece and it's not cost effective just to scrap the entire workpiece. So you'll bring it, you can actually alter the dimensions by rebuilding up that surface again, maybe like a flame spray application, which they have, and you end up then adding material, and then you can fix any mismachining that may have occurred. And then last but not least, it's going to alter the properties, right? So they either alter appearance, dimension, or properties. Sometimes it does all 3 with one surface treatment. But you can maybe improve the wear resistance. Maybe parts slide with other parts, and you want to go ahead and add maybe a hard anodize to the top surface there, so it's not going to go ahead and gall up the aluminum. Maybe you want to improve your heat resistance. You want to ceramic coat your headers or something like that. Improve your fatigue resistance as well, and corrosion resistance. So you can change a lot of the different mechanical properties of the part through surface treatments, some mechanical properties of the part. Now, with the first thing when we're talking about surface treatments is the workpieces. They have to be cleaned, and you have to remove any types of oil or foreign substances, such as like the cutting fluids, before you can even apply a certain surface treatment. So like plastic and ceramic and composite parts, they need to be cleaned before adhesive bonding. If you've ever tried to adhesive bond something with oil on it, it just comes right apart afterwards. The adhesive doesn't actually work unless you have nice, clean, prepped surfaces. So there's really 4 fundamental ways of cleaning a workpiece out there. You can either dissolve it, fracture it off, you could burn it off, or vaporize it. So we're going to talk about each one here. When we're talking about dissolving the contaminants off of a workpiece, there's really 2 major ways you can do that. You can put it in some sort of solvent-based solution. So that'll dissolve the contaminants from the surface without any type of heat. So a solvent tank, sometimes if anybody's ever had a parts cleaning or parts washer, where it's got some sort of solvent-based solution in there, and you put it in there, and you sometimes can just dip it in there and the solvent takes care of it. Sometimes the part's a little bit dirtier and you might need to use some sort of mechanical agitation to go ahead and take care of the dirt or the particles that are on that surface. It's really all that's on that surface are some sort of other particles other than the base material. Now, another solution to maybe dissolving it off to clean our workpieces would be an aqueous or a water-based solution. And they're going to use heat and detergents to dissolve contaminants. It's called a hot tank process. So here you usually have a liquid warmed up, a water-based solution. It's got detergents in there that help dissolve those contaminants from the surface. Now, if you've ever heard of ultrasonic cleaning, you can add in ultrasonic vibrations to this aqueous-based solution, and that'll end up is basically vibrating it, vibrating at high frequencies. And the little bit of mechanical vibration or the ultrasonic vibration helps the aqueous-based solution break down below the dirt particles and remove them from the surface of the workpiece. So we can dissolve it somehow, or we can wash it. Now, another way to do it would be to fracture it. So there's something called media blasting. It's called bead blasting. They have dry ice blasting if you're just using CO2, like to remove paint. But so they blast basically dry ice beads onto the part in order to remove paint. But that abrasive media fractures the contaminants from the surface. So you're actually fracturing off a top layer when we're bead blasting stuff and removing a small amount of material at the same time when we're cleaning it. So that may or may not be advantageous for your process there. We could also, so if we don't fracture it off there, we could vaporize it. So they have vapor degreasing with like triachloroethylene, and you could also burn it off like in a self-cleaning oven. So you can actually burn contaminants off the surface. But I'd say a majority of mechanical parts are most likely going to be some sort of ultrasonic cleaner if they're machine parts, or maybe a solvent-based solution. If you're going to fracture it off, that's a lot of times in repair and overhaul. If you're taking off paint that's already been on there and you need to repair and overhaul a part, you might fracture it off before you rebuild the part and so forth. Some parts get shot peened. We'll talk about that here in a little bit, but that's more of a mechanical surface treatment. We're not talking cleaning. We'll talk mechanical surface treatments with bead blasting a little bit later. So we can fracture it, vaporize it, or burn it off there. So I would know the 4 ways we can clean parts. Now, we're going to switch gears a little bit to more mechanical finishing of surfaces. Now, when you design a part, it's most likely going to have a desired surface finish or texture that's a requirement for function or sometimes for aesthetics, just to make it look good, right? So sometimes part of design is making the thing look good. But mechanical finishing is just using basically altering the surface of the part using some sort of mechanical action. So we're having some sort of tool or something contact the actual part here. And that's what mechanical finishing is all about. You have mechanical action of basically 2 contacting solids. So the first one, I mentioned this is a way of cleaning, right? So this is also a way of cleaning, but it's a way of changing the surface of your part as well. And it can also change the mechanical properties of your part, but it's known as particle impingement. It's abrasive blasting. So with abrasive blasting, we're using air pressure, and basically a high flow rate of air. And along the way, we have a little Venturi effect where we pick up some glass bead, walnut shells, or some sort of abrasive media to go ahead and impinge against the part. So in the case of like walnut shells, that's what they use sometimes to clean like brass. They use walnut shell blasting. So that's a softer media, but they go ahead and they shoot the walnut shells at the surface of the part at a high velocity, and that forcibly strikes that surface, changing the surface properties ever so slightly. It'll either produce a dull surface finish. You can clean your part a little bit depending on the type of material you have. But that's what particle impingement's all about, or abrasive blasting, is we're shooting the surface with some sort of abrasive type of media. Now, the popular one in order to change the mechanical properties is known as peening. Maybe you peened your welds in Kevin's welding class in IME 142 afterwards, and that's what we're really doing here with shot peening as well. But it's known as shot peening. It's a mechanical finishing here. So it's going to alter the surface by shooting little ball bearings or little beads known as shot against the surface of the part. What that actually does is it cold works the surface of the part, and it puts that surface in compression. So on parts that see a lot of cyclic loading, like when I used to build engines, we had our rods shot peened before we put the rods in the engine. And what that would do is we would take the connecting rod of the engine and it would go into a shot peening machine, which is a lot like a bead blasting booth, same thing, just different media. And we would basically peen the rods by blasting those little beads against them. The beads would basically come and cold work the surface of the part, putting compressive stress in the part. And as mechanical engineers, you should know the sum of the forces is always equal to 0, right? So if I have internal load on my part that's in compression, when I go to pull it into tension, it's going to have the net effect in tension is going to be a little bit less because it started out in compression. So peening basically is used in parts that have cyclic stresses, and it's going to go ahead and take that ultimate tensile strength. It's going to lower that ultimate tensile strength that the part sees a little bit because of all the cold work surface and the compression in the surface. So gears, connecting rods, they get shot peened sometimes. Just depends on the process. But that's what peening is and shot peening, if you're ever to wonder. It's a mechanical surface finishing process. Now, another one is called roller burnishing or burnishing, technically. So this is more plastic deformation of your workpiece. Remember, whenever we're cold working something, we're making it stronger overall to a certain point, right? But sometimes you cold work it too much, so we put too much stress in the part and it's no longer strong. However, when we're talking about roller burnishing here, which is a surface treatment process that's done usually on a machine tool, and you have hardened steel rollers now that are going to impart the surface finish. So what you have is you have a tool steel roller, and you're basically putting stress onto the part with these hardened rollers, which basically squishes down the peaks and valleys on the surface of that part, leaving a nice surface finish. So if you look, these are burnishing tools that I showed you. Here's one that's going to actually do an outside diameter right here. But you can see the surface finish before and after. For example, this might be a surface finish from maybe if we were going to go ream the hole, drill and then ream, you get kind of a torn surface finish like you see like there. But after burnishing, you get a real smooth surface finish, and you've cold worked the material, so it's got a little bit more compressive stress in there than it would have had before when we burnished it. So that's what burnishing is all about, if you've ever heard that term. Now, fixed abrasive texturing can come in all sorts. Maybe you've been to Chipotle and seen in the back of Chipotle the stainless steel that they have brushed. So they have really nice brushed stainless steel in all the Chipotles. And that was done with basically by fixed abrasive texturing. What they did is they took a Scotch-Brite pad, like you see down here, the red Scotch-Brite pad on the wheel, and they can scratch patterns into the sides, basically the sides of the material using an abrasive wheel or some felt, paper, or stone. So this is one of the most widely used techniques out there to kind of clean up materials. And we're going to end up putting a brushed finish. Maybe you've heard of it that way, a brushed finish on your metal. But we're going to put a brushed finish on our screwdriver bodies when we go ahead and manufacture the screwdrivers coming up starting next week in our face-to-face labs. So how you get that brushed aluminum finish or that brushed finish is like in the case of here, you have a wire wheel, and you can get that basically, you can get that abrasive wire wheel texture on the surface of your part by just running the wheel over the top of the part. So that's what sanding and brushing is, to get the brushed surface there. Now, if there's two other ones that we're going to talk about for fixed abrasive texturing or mechanical finishing. It's called honing, and then there's also lapping. These two processes, honing and lapping, are going to be covered in our IME 146 class. But what honing is for right now, it finishes the internal diameter of a part. So internal bores, and it's using fixed abrasive stones to put a final surface finish on a metal part. I'm not going to probably ask you too much more in detail about honing. We'll leave that for IME 146. But realize honing is a surface finishing technique. And so is polishing. So if you've ever used cleaner wax on your car, you've done some 3-body abrasion techniques or some surface finishing on your car. So here, what you're doing with that, with 3-body abrasion or polishing, is you have a polishing media of some sort. In the case of your automobile, it would be the cleaner wax. So there's abrasives inside that wax that are going to go ahead and take off little pieces of the surface of your paint, the clear coat. And when I start to wax the car, I'm basically pulling off all those peaks that are up there on the surface finish in order to get rid of them. So polishing kind of removes those peaks. And the cotton buffing cloth is nothing more than just to kind of rub those hard particles on that surface of your vehicle. At a certain point, once you polish it enough, you can polish swirls into it too. But at a certain point, once you get it all polished correctly, you then remove all the wax, or you remove basically those fixed abrasives there. That's all really polishing is you have a certain size of grit or abrasive grit, and you polish it down, and the finer your grit, the better or shinier of a surface finish you end up with afterwards. So that's all polishing is. You have to have some sort of media, you have to have the workpiece, the media, and then some sort of cloth to go ahead and apply the polish to. Now, the best surface finish, it would be obtained by lapping. And the lapping is another 3-body abrasion, or like a polishing method out there. And that's going to get you real flat surface finishes, real flat surfaces and smooth surface finishes. Now, if you've wondered how we make those large granite surface plates out there in the lab, they get lapped, their flatness. So they have that flatness, that high tolerance on their flatness, up to, I think, 6 decimal places on some of our surface plates there. So they're down there into the millions. But you use a lapping plate, which is basically nothing more than a cast iron abrasive plate that gets charged with lapping material, or gets the abrasive putty, or not necessarily putty, it's more like a paste. A lapping paste goes into that and on that lapping plate. And you can hand lap parts by moving them around in a figure-8 rotation on that cast iron plate. Or you can have a lapping machine where you actually put the parts down on the machine, and it provides the pressure and the rotation right there. So we're not going to worry too much about lapping in this class again, but realize it is a surface finishing technique, and we'll cover it when we talk about abrasives in IME 146. But realize it is 3-body abrasion. It mechanically finishes our surface. A very popular one out there for machine parts is tumbling. Has anybody ever had the rock tumbler? When they were a kid, they put a bunch of rocks and they sat there and tumbled on top of each other till they got real smooth. Same thing what happens with mechanical parts. So if you look here, we've got the tumbling media right here. That's what this green stuff is. So basically you have a large barrel. The media is what I circled there in green. You buy different types of media for different types of materials and surface finishes. You can get a polishing media, or you can get kind of a flat looking media like you see down there, or more of a satin look like you see in the bottom right corner on those parts. So what's happening is you're removing burrs and rounding over edges of your part with the tumbler, because the parts are getting vibrated in there with that media. There's a little bit of water in there as well. And the media is scratching the corners of the parts and basically just making sure that all the edges and the corners are nicely rounded over, so we don't have any burrs on our part. Now you can get different types of media where you can get a really shiny, you can get it to get a shiny finish, or you can get it to get a more of a satin finish. But that's what tumbling is. So you throw your parts in the tumbler afterwards, and they would sit there and vibrate and tumble until they're up to the desired surface finish. So we can basically go from the part that you see right here, where it's got a bunch of flash on it, down to more of this matte surface finish, because all the media hits up against these edges, and they actually put little dig marks and scratches right there from them impacting each other. So that would be another way to finish surfaces of the part, the tumbling method. Now, another type of mechanical surface is known as knurling. And everybody is in the face-to-face lab is going to go ahead and get to knurl their screwdriver cap later on in the quarter. Now, what knurling is you're producing a mechanical pattern, or cold working a mechanical pattern or texture into the surface of your part by pressing a tool into that surface. So the tool, in this case, basically like in the bottom right here, you'll see this is known as a diamond tool. So the diamond knurl has one set of knurling wheels on the top and one on the bottom, like you'll see right here. So there's one set of wheel, 2 wheel. You basically go push these wheels up against the part. The one set of wheels has basically slats this way. The other set of wheels has basically 45-degree angles this way. when they indent into the part, they end up with a diamond pattern because the one set goes that way, the other set goes that way, and you end up having this cross diamond pattern. And we feed the knurler down the length of our part and create this raised section on the actual part, like you see right there. So that's what knurling is all about. So it's a forming process. It's not a machining process. It's more forming, but it's a surface finish process that's very common if you needed a grip. And you really only knurl round parts. You can knurl flat parts as well. It's a slightly different style tool and setup. Are there any questions? Oops, you wouldn't have any questions because you're not there right now. So if you have any questions, you can shoot me an email or shoot your lab instructors an email. So that's what knurling is all about. Now, the last surface treatment we're going to talk about is electropolishing. So this is now an electromechanical process. So in electropolishing, you can see this part was electropolished. This is how it comes right out of the tank after it's done. But what you do is you place your parts on racks and you immerse them in an electrolyte. It's not Gatorade, but you immerse that in an electrolyte. And what happens is we have a potential difference in energy here. So the parts are the anode and they're positively charged, where there's a cathode in there, it's a cathode that's negatively charged. And that potential difference between the anode and the cathode allows the real small amounts of material to remove themselves from the surface of the part. So that basically, if I was to look at the surface of a workpiece, there'd be lots of peaks and valleys like you see right here. So what's happening with electropolishing is all these peaks basically get dissolved thanks to that potential energy difference right there. So it can remove tooling marks and deburr small specialized parts with electropolishing. So it's using electrical charge to remove that small little bit of material off the top of your part. Hence, it's an electromechanical process. So those are the major mechanical surface finishing processes out there. Now, we haven't talked about coatings yet. That's just what we can do to the raw material. We take the metal and we can go ahead, we can either electropolish it, we can maybe knurl it, tumble it, we could lap it, we could do some sort of polishing to it, we could hone it, we could sand or brush the surface, we could burnish it or particle impinge it. Those are pretty much all the major ways to treat the surfaces if you think about it. So at this point, we're going to now talk about protective surface coatings. Now, we're only going to cover the popular coatings used the most in industry. So we'll talk about anodizing, oxide, chromate, phosphate coatings for non-metallic coatings. Talk about some metallic coatings like electroplating, hot dip, and thermal spray. And then we'll talk a little bit about organic coatings like paints and powder coating. So, but they're broken down into three categories. They can either be organic, metallic, or non-metallic, these surface coatings. So we're going to break them up that way and talk about them. So the first one, organic coatings, you're probably familiar with. If you've ever spray painted anything, you've organically coated something. So paints, varnishes, lacquers, enamel, and epoxy coatings are available to protect surfaces. And there are a lot of different types of organic coatings out there to cover surfaces. I mean, it goes from the spray-in bed liner that you see up there in that truck, in the back of that truck. That's some sort of basically epoxy coating that they put in there in order to get a nice grippy surface on that truck. Then it goes down to the car body right there where we have the robot painting that red car. Gotta love red. But that's just a paint, right? So we're painting the part right there and we put a clear coat on afterwards and we're all set. Well, down here, sometimes we use epoxies or enamels, depends, to go ahead and wrap the surface of our wire. So if you look, this is in an electric motor. They went ahead and the wire windings, they put in an epoxy to kind of keep all the windings together right there so they can coat the surfaces and protect them. Then we have just a basic concrete, right? Epoxy right there coating that can go on the top of a garage floor or a floor of a shop. So there's all sorts of examples there. With these organic coatings, you want to go ahead and make sure you clean the surface very, very well before you apply any type of organic coating, or else it's gonna bubble up or have an issue afterwards. Now, one of the most popular organic coatings out there is a dry painting process known as powder coating. I would definitely know what powder coating is and how it works. But what we have here, in order to powder coat something, we have to apply a dry, electrically statically charged powder. So we're not actually painting with wet paint like we would on a traditional paint coating. So with powder coating, we actually charge the workpiece on a rack. So we put it on a rack and we electrically charge it. And then that charge allows particles, powdered particles, to stick to the workpiece without the use of solvents or water. So what I can do is I can spray it and the particles electrostatically stick to the workpiece, the metal workpiece. And at that point, I put it in an oven to bake on the coating. So it bakes on as like one surface coating. So it's just one type of coating. There's no what do I want to say on it? It's basically one full coat. There's no spots where you basically have brush marks or anything like that, because the entire powder coat is stuck to that surface fully in the dry form before you even put it into the oven. The cool part about powder coating is little waste, because I can reuse my overspray. So it's done in a booth, and I can actually take all the powder particles and put them back into my gun or reuse them afterwards if I have a way to go ahead and grab them back or to recycle. So there's little waste, and the part, once it's baked in the oven, it produces a hard enamel coating right there. And it's really, it's hard to go ahead and chip powder coat or scratch powder coat compared to a paint coating. Although it can be chipped and scratched, and once it's chipped and scratched, there's really no fixing it. You can't just use touch-up paint. It's a little bit different because it's an electric, it's basically one substrate that is formed a bond once it received that potential energy in the oven there. So that's what powder coating is all about. Now, metal electroplating. So we can put metal coatings on top of other metals, basically through an electrolyte there. So it's known as electroplating. This is how you gold plate something, how you silver plate something. If you've ever heard of gold plated, that's because the base material is made out of something different, and they just have basically a plating or a real thin layer of that metallic coating on the surface of the workpiece there. And how you actually electroplate something, you need an anode and a cathode there and an electrolyte, say, with your power supply there. So you basically put the part in there, into there, and the workpiece is the cathode, and it's plated with an anodic material. So we plate it with an anode, and so we go ahead and we negatively charge that workpiece, and then the positive charged anodes start to come over and stick to the actual surface of the part. So it's because it's performed an electrolyte of water, solutions, and salts, that metal ions can basically come off the anode into the electrolytic solution and then attach themselves to the actual cathode, which is the surface of the part. So we do nickel, chrome plating, copper plating, zinc, silver, and gold. So we usually plate it with some other alloy other than iron and carbon for steel. You don't electroplate with those types of materials. So that's what electroplating is all about. So you have a full metal coating on the outside surface of your part. It's fully plated. There should be no gaps in there. It's down to the base metal. Now, if you've ever heard of galvanic corrosion means you have two dissimilar metals, right, in the galvanic series, and one starts to corrode a lot quicker than the other, thanks to that galvanic series. Hence, that's why they have they have sacrificial anodes, like on the bottom of boats, like zinc and so forth. They have zinc sacrificial anodes. Well, that's what metallic coatings are doing, or hot dipping. Is usually you're going to take a steel or iron-based workpiece and dip it into a bath of molten metal that's going to provide long-term corrosion resistance. So that's whenever you hear of galvanized steel, it means it has a zinc layer coated on the outside of the steel layer. So they took the steel part and they dipped it into a molten bath of zinc. And then now the zinc's on the outside, and it's not going to allow the steel underneath to go ahead and corrode until you scratch off the zinc layer somehow or etch it off with acid. Now, if you ever have any type of metallic coated material like a zinc, you got to watch out when you're welding that kind of stuff. You can't weld harmful toxins that occur when you go ahead and you weld zinc or galvanized material. So you got to remove that top surface before you weld anything that has actually been hot dipped or anything like that. So it's providing a long-term corrosion resistance by basically putting the material, usually a steel or an iron, into some sort of zinc, tin, or aluminum there. It's called aluminizing if it's done in aluminum, which is kind of a rare scenario. It's only done in high temperature applications. Most commonly, they use zinc to do that, basically, to do hot dipping, zinc and tin. So that's going to be what our metallic coatings are all about. Now, another type of metallic coating, which is used a lot to build up, remember I mentioned you could build up work pieces. So if you see what they've got down there, they got a really large turbine blade, right? That part's probably not cheap. I guarantee that part's definitely not cheap. And if you had to go ahead and make another one of those because you damaged the fin on that part, it's going to be a lot more expensive than maybe taking a flame spraying application or thermal spraying application and depositing molten material on the surface of the part. So I can apply metallic coatings and I can apply ceramic coatings through plasma arc spraying, but it's known as thermal spray. So what I'm doing is I'm applying it to the top surface of the workpiece by basically spraying on molten droplets of the substrate, like molten ceramic droplets or some sort of molten droplets of the base metal that I'm building up right there. So in the case of flame spraying, they're basically rebuilding or worn surfaces or fixing machined surfaces by spraying on metal material or little metal droplets onto the surface of the part to add material. Then I can go ahead and machine that right back off. So some more expensive parts definitely use this process. I've seen it used a lot in the Caterpillar proving grounds, or not proving grounds, the Caterpillar repair and overhaul. They have Empire Caterpillar in Arizona, which they would basically repair larger shafts that are hardened shafts that they needed to go ahead and repair for the bulldozers. They would go ahead and rebuild up using the flame spraying process some surfaces on that shaft so they wouldn't have to go ahead and rebuild or remanufacture a whole brand new shaft. So it's a way of fixing stuff. Now, in the case of like ceramic coatings, sometimes people put ceramic coatings on top of things to alter the properties of like the headers. For example, you can keep heat in with a ceramic coating on your headers. The hotter you keep your exhaust manifold, the faster the gases are going to travel through there, right? So sometimes it's good to have hot exhaust manifolds. And sometimes you ceramic coat them in order to kind of keep that in there. And to do that, they use plasma arc spraying. So they're going to need to generate more energy than the flame can generate in order to melt the material. So they use a plasma arc to go ahead and melt the material, the ceramic material to add on the surface of the part. But it's called thermal spraying. So that's going to be a metallic, basically a metallic coating, or it could be a ceramic coating. Now, when we're talking about non-metallic coatings, anodization is one of those. Aluminum has a great ability to develop a thick oxide coating on the outside of it when I go ahead and expose it to an electrochemical cell. So here, when I have aluminum, I could either do hard anodize or color anodize with aluminum. Now, hard anodize, you get black and you get a little bit thicker aluminum oxide surface than you would say on color anodize. Now, color anodize, I can get pretty much any color under the rainbow. You can kind of see some parts right there. And what's going to happen is I'm creating an aluminum oxide layer on that surface, which is a very hard ceramic. So I'm creating a ceramic layer on the surface of my aluminum through a process called anodization. Now, most common on aluminum, but you can anodize titanium, magnesium, and zinc parts as well. But realize it's primarily done on aluminum. Now, there's two types of anodization. I mentioned there's colored anodize and there's hard anodize. Color anodize is going to be the thin anodization, and that's only going to basically penetrate the surface by about 1/3 of a mil. So the surface grows by about 1/3 of a mil, and it's be about a 1 thou thickness overall in the coating. So it's typically used as a decorative finish, and dyes can be added to control your color. You can actually get them to change color if you have a really good anodizer throughout the same part. Now, most parts that have a lot of wear, issues with wear, they're most likely going to be hard anodized. This is a mil spec thing. So the part's going to grow by about a half of the anodization thickness with hard anodization here. So that means if I'm worried about the overall part size in the long run, I got to make the part smaller because the plating is going to add material. All platings and surface treatments add material to your workpiece. You've got to be worried about that not fitting into the assembly after you paint it. So definitely look at how much your process is going to add in terms of thickness to the surface. Powder coat, basically metal plating, all of these, I'll add a little bit of material there. So these hard anodized parts are usually done on hardware resistant surface on machine parts. Like you're going to see, there's lots of parts to get hard anodized out there. Now, when I'm talking about the difference between the two, what's happening is the part to be anodized goes in with a lead cathode. So we have a lead cathode, we have the anode as the part, we have a potential difference between them. And you usually put some sort of sulfuric acid now. So you put the part in acid and then you give it that potential difference of energy. And that's going to have basically this aluminum oxide coating occur on the surface of the part. So some of it goes down into the surface of the part, right? Or off the surface of the part, but you have a buildup of about a 1/3 of a mil right there. So it's usually about a thou right here, that thickness. Now, when you have your hard coating, you usually have about 2 thou that's going to basically come up right there. That's going to come up there. So about 2 mils or so. Does that make sense, everybody? So you got to have about a 3 thou thick anodization here on the color. 1/3 of it is above the surface, 2/3 of it's below the surface if it's 3 thou thick. Now, if it's hard anodizing, it's going to be a little bit thicker, maybe 4 thou thick, and about half of it's building up surface. The other half's into the part right there. So you have to be worried about this adding material to your part and not fitting in the assembly anymore if you're doing anodization. Now, there's some other stuff out there that's used quite a bit, and they're called they're non-metallic chemical coatings. It's known as chromate coating. So with chromate coatings, surface conversions used on aluminum, zinc, cadmium, magnesium, and it protects surfaces from corrosion. So maybe you've seen a lot of military parts with this kind of olive green, right? That's because they are basically chromating the surface of the part so it can withstand basically the environment that it's going to be in, the chemical environment that it's going to be in. Now, sometimes you're going to see that chromate or the chromate coating as a gold coating right here. So what we're doing here is we're dipping parts in chromatic acid. And so there's chromium salts in there, and the reaction is going to create a film on the surface. I forgot the exact chemistry behind it. It's aluminum. I forgot it exactly off the top of my head, but you can get shades of yellow, bronze, and green. All of are black with these chromate coatings, or basically, it's basically called chem film. So you can do chem film, if that's kind of the industry term for it. But I would know that there's chromate coatings and known as chem film. Now, steel parts, mainly iron or steel work pieces, it can be also done in copper and stainless, can get what we call an oxide coating. You've heard of bluing, that's the same type of thing, it's an oxide coating. And what we're doing with this is we're using a chemical bath, so chemical salts, and we're producing corrosion here. So we're actually creating an oxide corrosion, and we have an extra iron and an oxygen in this one. I think it's Fe4O3, where rust is Fe3O2. Fe3O2, I think, is iron oxide, is going to be that. So it's basically got one extra iron and one extra oxygen in this coating compared to rust. And it leaves a black surface on the top of your part right there. So because this is an oxide coating, it is rust coating basically, but it looks better. It's basically got more resistance than the regular part would have, but parts can still rust or corrode with a black oxide coating because technically it is a corrosion on the surface that we already produced. So don't think because the parts have been black oxide coated, they can't rust. It will rust. It's just not going to be as fast as it having the base metal, the base iron or steel work pieces there. So that's what a black oxide coating is. It's another type of non-metallic chemical coating where we're creating basically a layer of oxides or corrosion on the surface So it slows down the corrosion. Now, that's all we're going to talk about in terms of surface treatments. We are going to change gears here completely to geometric dimensioning and tolerancing. So I would take away the major surface treatments and just know a little bit about each one of those surface treatments, especially, and then look at your homework questions that I'm going to ask you this week. Those are going to be what you're going to be asked most about on the final exam. So I would just study what the homework asks if you're worried about surface treatments in the final. But today, now, we're going to finish up. I'm going to try to explain to you why GD&T, or geometric dimensioning and tolerancing, which is known as GD&T, is so popular for mechanical engineers to learn about. Now, what GD&T can do is it can help us control what we call extreme form variation. So if we have a part and our part has a tolerance on it, the limits of the tolerances right there, the limits of the part's tolerance, are known as maximum and least material condition out there. So if I had this part right here, and it was this hole, it was made at 25.1 to 25.0, and my maximum material condition would be when the hole's the smallest, it's when it's 25. My least material condition was when the hole's the largest, to be 25.1. Well, if I made my part to be within tolerance right here, and I didn't have any GD&T on it, I just had this regular diameter right here, I could still sell this part if I made the hole 25 at the top, 25.1 at the bottom. Now, it's no longer a hole, it's more of a cone, right? If you think about it. And what GD&T can do is it can go ahead and help me prevent what we call extreme form variation. So when a feature varies from its limits to size between MMC and LMC, we're getting some extreme form variation on that feature in our part and in our design. So to prevent that, we can add geometric dimensioning and tolerancing controls to our part here. Now there's only 14 symbols. Now back in my day, there was 14 symbols. Nowadays, there's only 12. But so there is 2 symbols that went away, symmetry and concentricity. So we don't have to worry about those too much. We did everything done with true position. That was symmetry and concentricity in the past. I don't expect you to remember that little bit of a detail, but I still show symmetry and concentricity in case you see them on a legacy drawing out there. But what GD&T does is it can control extreme form variation and make our parts that we can go ahead and communicate our design intent as a mechanical engineer for that actual part to whoever's making it. And I can do that by applying either straightness, flatness, circularity, cylindricity, profile of a line, profile of a surface, true position, parallelism, perpendicularity, angularity, run out, or total run out to features on my part. Now, when I have something called GD&T, I go ahead, all I'm trying to do is use it to go ahead and control form and location of the major features on my part. So remember, everything's got a size and a location on a part out there. And your goal is to get your part made correctly after you've designed it and made the drawings as an engineer. So you may need to establish something called a datum to relate to the function of the part. What a datum is basically one of the major features or surfaces on your part you like to compare other features off of, or the size and location of things off of. And so it's going to help by using GD&T instead of using conventional dimensions to go ahead and confine everything. It's going to help lower your manufacturing costs and then control that extreme form variation there, and possibly give the manufacturing engineers a bonus tolerance for a feature if it's not produced at the limits of size. And that's what we're going to go through today and talk about is bonus tolerances and how we can get more tolerance or how bonus tolerances actually work. Now, if I have something called a datum is specified on my drawing with the datum feature. So in order for an engineer to specify an important surface, plane, or point, they either need to use a datum feature symbol like you see right here, or a datum target symbol right here. Now these datums, They're letters to identify it, like A, go down the alphabet, B, C, D, E. So you just work your way down the actual alphabet once and you start with A. So that's all datums are, perfect surfaces, planes, points, or axes. I can relate GD&T callouts to. If I'm not using a datum for a GD&T callout, I don't put a datum feature or target on my part. I have to go ahead and call out a datum in a GD&T callout if I'm going to go ahead and have it on my part. Otherwise, you wouldn't have it. Why have it? Now, a lot of the times, these datums, as the engineer, you're going to establish these datums. And there's many concepts to keep in mind while establishing datums, such as like, what's the part going to do? Where's the main surface you want to relate stuff off to? Or you can think about your manufacturing processes. How do I want them to hold on to this? I specify this as my datum and base things off of it. Chances are when we're machining it, we're going to hold it by the datum, make the datum the work coordinate system, and then base our CNC program off of that 0 point that you specified. Now, if I wanted to make the surface a datum, I just put it in the view where the surface appears as an edge. So it's really the bottom surface of this is my A datum of that block. So that's one way to specify a datum. If I want the centerline axis of a dimension to be my datum, I put it directly in line with that dimension. So because this diameter out here, this would be the diameter dimension, whatever size it is, because this datum is in line with it directly, I know the datum is the centerline axis of my part. So usually on round parts, you make the datum the centerline axis, and prismatic parts, you make some sort of major flat surface of the main datum that you base everything off of. And from that, that's going to set up basically that every single dimension originates from the same reliable location. Because out there, we have 6 degrees of freedom that every workpiece has to go ahead and have constrained before we machine it. If we don't constrain all 6 degrees of freedom, we're never going to have the same XYZ0 when we put the parts into the CNC machine over and over every single time. So if you think about it like on my phone, I have the primary datum establishes 3 points. I set up a plane that my phone sits here in space, right? Well, the secondary datum's 2 points, a line, it takes away 2 more degrees of freedom, and I really only have then a tertiary datum stop, which locates it it locates all 6 degrees there. So I'm able to get the same XYZ0 by establishing at least 3 datums, maybe 2 datums on an actual round part. Because on a round part, your primary is usually a back face of something, and then your secondary and tertiary are the centerline axis, like you see there. But this is the standard way parts are designed and machined and inspected and out throughout the entire world, is we set up datums and we take measurements from datums for different part features. Now, hopefully you understand what a datum is. And I'm now want to explain a little bit about the 5 types of GD&T characteristics so you know about them. And then I'm going to talk about location of the features pretty much. I'm going to talk about locations and we're going to call it a day for GD&T. We'll learn more about it as we go through in IME at the end of this quarter, and also in IME 146, we're going to do a lot more with GD&T. But these geometric characteristic symbols, they're grouped into 5 different categories. So I could either have the form of an object, the orientation of an object, the profile of an object, run out, or a location out there. So, and remember, concentricity and symmetry are gone. So this is how they're grouped. Form tolerances don't actually relate to datums. So it's for individual features. We don't relate to datums here, no datums. It's just how perfect of a form do you have? How perfectly straight are you? How perfectly flat are you? How out of round are you? Or how perfectly cylindrical are you? So we got straightness, flatness, circularity, and cylindricity. Now, those are going to be form tolerances. Well, not everything in the world's made with just a full circle and a line. Sometimes we have arcs. So we can describe everything with a line and an arc. So when I have profile tolerances, you describe how perfect of a profile you have with basic dimensions then you inspect to see how far off your profile is from the perfect profile. Those are heavily used those are heavily used callouts out there, and they can either be related to a datum or related out there in space to themselves and not oriented to a datum. That's why it says for individual or related features. Now, the last three, orientation, location, and runout tolerances, require datums to go ahead and orient themselves off to or locate themselves off of. So with orientation in mechanical engineering, you can only be oriented three ways. You could be parallel, perpendicular, at some sort of angle. And that's what the orientation tolerances give me here. For location, you used to be concentric and symmetrical. Now we just position everything with this position. And we're going to talk heavily about location tolerances. And there might be a little location tolerance example on your final exam that you're going to have to do. Then last but not least, we have something called runout. What runout is how wobbly we are about our central axis of rotation. So it's technically checking for circularity and where our center of our axis is in relationship to the outside of the part. So it's looking for the wobbliness as I rotate the part around its central axis. Now, so I would just kind of know those 12 different symbols, what those 12 different symbols mean, and realize you can't really specify GD and T without specifying it in a feature control frame. So what we see right here is the size of the hole, and then this is the location for the feature. So this is a feature control frame, and the feature control frame has the GD and T symbol in the beginning. It has a tolerance next, and then any datum references that basically pertain to that call out right there. So we're going to learn how to read this feature control frame as we work through this lecture here today. Now, in this feature control frame, does everybody see I've got these modifiers, these material condition symbols? Those are known as modifiers because what they actually do is they modify our tolerance. I can now have a dynamic tolerance. I can use these material condition symbols to hold my tolerance when my hole is the smallest and basically open it up as my hole gets larger. So they're used in a feature control frame to go ahead and give me a bonus tolerance zone when I'm manufacturing. We always love bonuses, right? Especially at the end of the year. So what it's going to do, it's going to establish the relationship between the size of the feature with its given dimensional tolerance and the tolerance zone size. So they modify the geometric tolerance, these material condition symbols. So what you see right here is I have one down here for the slot. Let's just talk about that one. So you'll see I have an MMC symbol right there. Well, if I have this part that's 1.000 plus or minus 0.004, I know that my maximum material condition, MMC, whoops, sorry, that was supposed to be a C, is equal to 0.996. That's when the slot has the maximum amount of material. Then I have an LMC, which is going to be equal to 1.004. Well, this 2thou positional tolerance is only held when this is at its maximum material condition right here. So really, the tolerance zone has to be 0.002 when it's at 0.996. However, when I start to go away, I make my slot wider. Let's say I make it at LMC. I am 8 thou away. I could have my tolerance zone size at 10 thou and still be good. So my slot can slide around about 8 thou more than it could have when it was in the 2 thou position. So that's how a material condition symbol modifies our location tolerances. So based off the produced feature size, I've got to hold that 2 thou tolerance at MMC. But as my slot gets larger, my amount of wiggle room or my location could be a little bit larger as well. And that departs with the amount that we take away from the actual size tolerance. So these material condition symbols, whenever you see M, it holds it at maximum material condition and it opens up that tolerance zone, the amount that we departed from the maximum material condition. So I'm going to do another example with you. Don't worry. If it's held at LMC, it would hold it at least material condition. This is used to control minimum wall thickness of a part. If that's what's important in your design is minimum wall thickness, you can do that with the LMC symbol if you have a hole that's placed really close to it. Now, the only place that you're going to find these tolerance modifiers is in this feature control frame. So if I have a positional tolerance like you see right here, this is the tolerance zone that I have to be within. I'm holding it at maximum. And then these datum references tell me what edges or surfaces that feature is located off of. And that's what a positional tolerance is all about. It's called, you set up where you want true position to be on your part, and you inspect how far you vary or you differ from the true position. So really, we're taking a different look at how we're dimensioning things now. We're specifying exactly where the true positions need to be. We inspect to see how far out we are from that true position. That's what location tolerance is all about. And they're great in mass production because they're giving us a bigger shaped tolerance zone as well. So I'm going from a round tolerance zone to a square tolerance zone, or I'm going from a square tolerance zone to a round tolerance zone using location tolerances too. So if we look right here, we have this material condition symbol. Let me go a little bit further actually to show you this. Next slide. I have, with a positional tolerance, I have a round tolerance zone here. Well, before, when I had a conventional tolerance zone going from an edge, you'll see it basically just gives me a square zone. The thing is, with this square zone like that, it's not as accurate as a round tolerance zone. Because if I had a round tolerance zone, let's say I made the center of the hole right there. The distance between there is less distance than it would be to the corner right here, off center. So I should still be good if I'm in this area right here, right? For fitting parts together. So what positional or conventional tolerances do is they take your square tolerance zone, they turn that into a hypotenuse right here to figure the hypotenuse of the two sides of the square. And that's now the diameter of the zone that the part can fit within. So we're getting 54% more area to go ahead and make our features with size. So instead of having a drawing like this, where we have the plus or minus 0.25, I can give basically an example here where I have 15 plus or minus 0.5. So this is the size. This is the location down here, right? So the location is based off its position, is the location of it. It is perpendicular to the primary datum, located off of the secondary and the tertiary datums. So if we look, this tolerance zone, the cylinder, is perpendicular to this A datum. So it's perpendicular to the A datum, and it's located off of B and C, like you see right there. So I have basic dimensions which locate where my true position needs to be. And that sets up a diametrical tolerance zone right here that is 0.7 at the maximum material condition. So if I had something where I had hole size, and then I had over here tolerance zone size, check this out. If my hole size, let me come back a little bit more. If my hole size was 14.5, my tolerance zone size would be 0.7 because I'm at maximum material condition. Let's say I produce one of the holes at 14.8. Well, I'm 3 thou away from my maximum material condition, so I'd be 1.0 for my tolerance zone size. I add the amount that I'm away to my tolerance zone. So if I'm at 15, right here, I'm basically 0.5 away, so I'd be at 1.3 for my tolerance zone size. Then if it's at 15.5, I would basically be at 1.7 tolerance zone size, like you see right there. So literally, that's how the tolerance zone size gets larger, or I get bonus tolerance based off that material condition. So you can see why mechanical engineers and industry uses this, right? Because you set up the size limit when it's at the features at its maximum material condition, and for the parts to fit together. Then as the hole gets bigger, I might as well be off by a little bit more, allow it to be off by a little bit more, because more parts will pass the quality control stage. So it's a way of technically doing dynamic tolerances, and I guarantee this is what industry uses over conventional dimensions. I promise you. So that's what locational or conventional tolerances are all about. Hopefully, this week in lab, we're going to be finishing up our last week of lab. We're going to go for mill project and lathe project 1. We're going to go into the screwdriver that's going to be starting next week for Thursday labs. Next Tuesday lab, you still have your mill and lathe project 1. But this week you have an assignment. Let me go to that real quick. That's going to be up on Canvas. Give me 1 second. I actually don't want to show you my email that's up, so let me do that. New share there. We'll go here, share. And I'm going to run over here to your Canvas assignment. So we'll go to Canvas. I want to point out, we'll go to 145.01. So you have week 5's Canvas assignment that'll be due next week. And it's going to talk a little bit about GD&T. I want to preview it real quick. You're going to see down here, it's just basically going to ask you about material condition symbols. It's not going to ask you a lot of details about the GD&T is what I wanted to get to. So I just want to know why they're advantageous. I'm not going to ask you to go ahead and calculate at this point right now. That might come up on the final exam, but I'll do a really good final exam review with you during the week 9. We're going to do a final exam review, and I'll go over every single question on the final exam, I promise. So make sure you get this in, work on this assignment here that'll be due in 1 week from today, or 1 week from whenever your lab is in week 5, and you have a great week. And if you have any questions, I believe I put my office hours up on the Canvas in the chat up there when I left an announcement a few weeks ago. So stop by my office hours or stop by your lab instructor's office hours, and have a great day, everybody.